Hello everyone, myself A.Yadagiri, faculty of BEE and also the assistant professor, Department of Electrical and Electronic Engineering, MLR Institute of Technology, Hyderabad. In the last session, we have discussed about the analysis of the RC series circuits. So in that, we have discussed about the how much amount of voltage applied to the RC circuit, and based on that, how much amount of resultant current is coming from the network, and based on that, how much amount of phase angle maintained by the voltage and current of the RC circuit, and how much amount of impedance offered by circuit. So these so many things we have analyzed in the RC series circuit in the last session. So in this session, we are going to discuss about the analysis of the RLC series circuits. So in the RLC series circuits, so we need to take the overview of this one. So in this the RLC series circuit, we need to analyze about the RMS value of voltage and also the RMS value of current, and based on the RMS value of voltage and current, how much impedance offered by the circuit, and based on that, how much amount of instantaneous power and also the average power taken by the RLC series circuit. And then how we are going to plot the phasor diagram of the whole RLC series circuit. So it has to plot between, the phasor diagram of the network should be based on, should be plotted between. So that is a voltage across the resistor, voltage across the inductor, and voltage across the capacitor. So and based on this one, then how much amount of phase angle maintained by the voltage and current, and based on that one, how much amount of power factor should be taken by the or should be given by the RLC series circuit. So based on that, we need to get this the voltage and current waveforms of the whole RLC series network. So these many things we need to discuss in this session. So now we need to go with this concept, that is, so let us consider a resistance of capital R ohms which connected in series to the inductance of the capital Henry, and the whole combination is in series to the capacitance of the capital F farad, so which are connected to the alternating voltage source, that is in terms of RMS. So this RMS voltage drive the RMS current is capital I. So the both quantities, voltage and currents are we need to consider as in terms of RMS only. So here let us apply the voltage to the network, that is RLC series network. So that voltage is a RMS value of voltage. It is RMS value of voltage, then which drives the or which gives some resultant called RMS value of current. So that is RMS value of current in terms of ampere. So here VR is a vector and also VL is a vector, and as well as VC also vector. So here VR is the voltage drop across the resistor, and VL is the voltage drop across the inductor, and also VC is the voltage drop across the capacitor. So for that we need to take VR. Here VR is a voltage drop across the resistor. So in terms of Ohm's law, we can expand this, that is I into R. So in case of this one, so the voltage and currents are, so I and V's are in phase. So both are going to in same phase. So with reference to the current, the voltage of the network should be in phase. This is VR. Now coming to the other vector notation, that is a VL. So here VL is the voltage drop across. VL is a voltage drop across the inductor. It is. We can also expand this one. So that is VL equal to, it is I into XL according to Ohm's law. It is V suffix L means V voltage across the inductor. So with reference to the current, the voltage should be voltage should be always voltage should be leading in this case. So for that V leads the current. V leads the current an angle of 90 degrees. So with reference to that one, this is the current as a reference. So in case of inductor, the voltage always leads ahead that an angle of 90 degrees. This is a V. Then the last one is a last vector of the last phasor is a VC here. So where VC is the voltage drop across the capacitor. It is voltage drop across the capacitor. So we can say, we need to represent that one is in terms of VC. So VC equal to according to Ohm's law I into XC. So in this case, current or voltage. So take always V means So here V always, voltage is always lags the current, that is capital I, lags the current an angle of, by the angle of, otherwise an angle of, so 90 degrees. So lags the current an angle 90 degrees. So for the phasor diagram of the capacitor here, so this is the voltage of the capacitor, so it is a V. So current is always leads ahead, that is I 90 degrees. So this is the phasor representation of the pure capacitor case. So for the RLC series circuit, we need to plot the phasor diagram with help of all phasor quantities like VR, VL, VC and V. So why should we take this all means? So it is a electrical all parameters, like V is electrical parameter, I also electrical parameter, VR, VL, VC. So these all electrical parameters are so taken into account to analyze the required things are difficult. So that we need to keep this all electrical parameters are in the phasor notation. So it is a mathematical notation. So if you are able to analyze the required things by using the mathematics, it is easy thing. So that we can represent the all electrical parameters are in terms of the phasor diagram. So need to draw the phasor diagram of RLC series circuit. So draw the phasor diagram of RLC series circuit. RLC series circuit. So with the help of VR, VL and VC, also the capital I. Current is a same means current is the same means, so capital I also we can consider. So we did not consider the voltage. Why? Because it is a vector sum of the phasor sum of the that is a VL, VR, VC. So that's why we can only consider about the VR, VL, VC. So further we need to take the reference as current only. So this is the reference vector as current. So this is a current is a vector. Current vector is a reference, because current is a constant for each and every element. So that we need to take the constant parameter as a reference. So with reference to the current, the voltage across the resistor is in phase. So that we need to take to represent that with the different color. So this is the voltage across the resistor is this one. So this is the VR, we can say. Now coming to the voltage across the inductor. So with reference to the current, the voltage across the inductor should be always leads ahead the current. So I want to change the pin color to represent the phasor. So this is the voltage. This is the voltage across the inductor. So this is, we can say, VL. So with reference to the current, the voltage across the inductor always leads ahead that. That's why it's a VL. So now other one is the last one, capacitor. So the capacitor is always lags the voltage. So the capacitor is always lags the voltage. So at an angle of 90 degrees. Lags the voltage with the current at an angle of 90 degrees. So for that we need to change again the color of the vector. So this is the capacitor voltage. So that is a VC. So this is VC. VC always lagging, VL is always leading. So based on that one, we need to plot the resultant vector. So based on the type of network, if it is a pure if it is a inductive dominant network, so we can consider the dominant parameter we will get, or the dominant vector we will get on the inductor voltage. To say based on the network. So either the effectively inductive or capacitive, depending upon the voltage drop across the element. So if it is a inductive network, the voltage drop should be more than the capacitor. So the more predominant term in this case means either the VL or VC. The voltage drop across the inductor is the most predominant term. Then the corresponding network is the effectively inductive network. So the most predominant term is the VC, means the voltage is the voltage of the network dominated by the capacitor. The voltage across the capacitor should be dominate the inductor voltage. Then so the most predominant term is the VC, means the corresponding circuit should be effectively capacitor network. So based on that one, so we need to take the most predominant term in this case, VL greater than VC. VL greater than VC. So for this case, it is a purely, effectively inductive network it is. So for that, the resultant vector should be so the resultant vector should be here. So we will get the resultant vector. So here, these two values are same only. So we need to take the resultant vector on inductor vector, inductor voltage. So this is the resultant vector. It's a V. So this value is a VL minus VC. In this case, VL is greater than VC. So based on the voltage across the element, so this case we will get, either the inductive network, either the capacitor network we will consider. So if the voltage across the inductor is more than the capacitor, then the effective network should be purely inductive network. The most predominant term in this case is the VL. So if the network has, the voltage across the capacitor should be more than the inductor, then the corresponding network should be effectively capacitor network. So in that case also we need to plot the phasor diagram, that is a VC greater than VL. So most of the cases we need to consider this one only. So the most predominant term is the VL, so that VL is greater than VC, means the corresponding network should be the inductor network only. Dominant voltage in the network should be voltage across the inductor, that is only, so the inductor network. So for that, the required voltage or the applied voltage of the network should be, so on VL only we will get that. So this value should be difference of this one, because these two are same. So based on that, so we will get the resultant value. Resultant vector should be, so on the inductive vector or on the VL, that is V. So this point we can consider as a O, and this point we can consider as a and so this one we can treat as a B here, and this one we can treat as a C, and this term is on this point we can consider as a D. So this is the case number 1. Other case also we will consider, but the case number 1 we need to consider most frequently. More frequently we need to consider this case only. So for that only we need to take the resultant vector on VL. So also we'll get the resultant vector on VC. So based on this condition, so the more predominant term on the network should be either the VL or VC. Based on that, we'll get the resultant vector. So this is the phasor diagram of the RLC series circuit. First, we need to take the current as a reference. So with reference to the current, the voltage across the resistor is the in phase, and with reference to the voltage across the resistor, the inductor should be, with reference to the current, the inductor should be always, the inductor voltage should be always leads ahead that. So for the capacitor, the voltage across the capacitor always lags behind the current. That's why we'll get the, so the voltage across the resistor is this one, and the voltage across the inductor is this one, and the voltage across the capacitor is this one. So in the RLC series network, we need to determine the resultant vector. So we need to consider the two different cases. So that is decide the voltage across the different element. If it is a voltage across the inductor is greater than the voltage across the capacitor, so the most predominant term is a VL. That's why, so the resultant vector we will get on the voltage vector, voltage across the inductor vector in the phasor diagram. So if the most predominant term of the network is a VC, means VC is greater than the VL, means the resultant vector we will get on the VC. So the most of the cases we need to consider this one only. For that we need to plot the resultant voltage on VL. So this is the phasor notation of the voltage and currents of the all element like RLC. So this angle is we can call pi. So from the phasor diagram, so we need to do some further analysis from the phasor diagram. From the phasor diagram, so right angle triangle, according to the right angle triangle OAD. So according to the Pythagoras, it is used to write OD square equal to the AD square plus AD square plus OA square. So OD square equal to the AD square plus OA square. So for this we need to find out the resultant current circulating to the network due to the applied voltage. So again triangle OAD, according to the Pythagoras, that is a V square equal to VR square plus VL square minus VC square we got. Means it is VC. So VC means it is a minus VC. Why? Because it's a lagging. Means the expansion of this one is minus x into minus I into xc. So it is a leading, means I into xl. Plus we can consider. Leading means plus, lagging means minus. So for that we will get here minus VC square. Both are going to get whole square, that is VL minus, so VC whole square. So here V square equal to square root of, again to the Ohm's law we can expand this, that is IR whole square plus I into XL minus I into XC whole square. So the I square is a common term, so it is R square then XL minus XC whole square. So we got here I only. So then the network current is I equal to, so we can write V divided by the square root of R square plus XL minus XC whole square. So from the phasor diagram, so we have determined about the RMS value of current. So in this we got some unknown thing, that is called, so the square root of R square plus XL minus XC square. So that we can say that the term square root of R square plus XL minus XC whole square is opposing the flow of alternating current. Is opposing the flow of AC current. Flow of alternating current. So combinedly it is called impedance of the network. Is called as impedance of the RLC series circuit. Is called as impedance of RLC series circuit. So we can represent the third term with the capital Z. So finally the corresponding network current should be I equal to V by Z we can write. So where Z equal to square root of R square plus XL minus XC whole square. So the XL is the inductor reactance of the network and XC is the capacitor reactance of the network. So there are two different parameters we have obtained from the phasor diagram. So both are electrical parameters, but we have determined these are from the mathematical notations or mathematical representations, that is the phasor diagram. So then also we need to determine some more parameters from the phasor diagram. So that is a phase angle. So that is a phase angle. So the phase angle notation is a phi. So the phase angle notation is a phi. So from the phase angle, it is clearly noted that are clearly saying about the phasor diagram. So that is the voltage of the network or the voltage of the circuit. So the voltage of the circuit always leads ahead the current at an angle of 5 degrees. So means the phasor diagram clearly saying us that is the current of the network always lags the voltage at an angle of 5 degrees. So we can say right here like the current of the network always lags the voltage at an angle of 5 degrees. So for that we need to determine that angle how much, the phase angle or power factor angle how much we need to find. So for that we need to consider again, so triangle OAD. So triangle OAD, so tan pi value we want to write. So tan pi equal to, so that is the triangle OAD. So this is a triangle OAD. So from this one the tan pi value, so tan pi equal to, so we want to write it's a ratio of the, so AD upon it is a OA. I mean to say opposite side upon the adjacent side. So for that AD upon OA. So it is a AD upon OA. So the expansion of AD is VL minus VC upon VR. VL minus VC upon VR. So if you are able to expand the whole terms with the help of Ohm's law, which means I into XL, then I into XC, so divide by I into R. So both IR gets cancelled, then tan pi equal to XL minus XC upon R. So then the phase angle or the power factor angle between the voltage and current should be tan inverse of, it is a XL minus XC upon R. So this is the phase angle, so maintained by the voltage and current of the RLC series network. So it are also determined with the help of phasor diagram. So that's why, so pi equal to tan inverse of XL minus XC upon R. So this is the phase angle. So based on this one we want to write the instantaneous power. So instantaneous power we have already determined for the case of RL and RC will get similarly. So the the average power taken by average power, so consumed by the RLC series circuit. So that is a P equal to VI cos phi only. So why? Because the in case of the pure inductive case, the average power consumed by the network should be 0, and also similar to the capacitor also be 0. Due to the resistance added to the LC series circuit, then the average power taken by the whole circuit should be, that is active power only, that is VI cos phi only. So this is P equal to VI cos phi. So till now we have discussed about the voltage taken by the voltage taken by the network, and also the current supplied to the network by the voltage source. Then also the how much amount of impedance offered by the network. So that is the square root of R square plus XL minus XC whole square. Then based on that we also determine the phase angle, and after that we also determined about the phase angle, the power factor angle, and also the average power taken by the network. And for that we need to take the power factor of the network. So power factor of the network, that is cos phi equal to, again it is a ratio of the resistance to the impedance only. So ratio of the resistance to the impedance from the power impedance angle, that is R by Z we can say. So these many things till now we have discussed. In the RLC series circuit we have been noted about the 3 different cases. That is the case number 1 is, so I mean to say in the RLC series circuit we have the 3 different cases. That is, so the case number 1, first case, I mean based on the impedance offered by the network. So what is the impedance of the network? That is a Z equal to the square root of R square plus XL minus XC whole square. So based on the impedance offered by the network, so we need to consider the 3 different cases in case of the RLC series circuit. So that is a case number 1. So when XL greater than XC, the case number 1, when XL greater than XC, so that is XL minus XC term. So in the impedance, the XL minus XC term. So in the impedance term, so if the network has XL is greater than XC, that is we can say XL minus XC is positive. So in this case the whole term, I mean in this term, so if it is greater than, I mean if it is present the domination of the inductor reactance is on capacitor reactance, we can say XL is greater than XC. So in this case the whole term is going to get positive, I mean the XL minus XC term is positive, and the phase angle of the network also should be positive. So the whole circuit should be behave like a, so at this instant the whole circuit should be behave like a RL series network or RL series circuit. So in the impedance term, XL is greater than XC, so the whole term will become positive, and the phase angle of the system or phase angle of the network also going to be positive. Then the whole system or the network should be behaving like a pure RL series network. So in this case the voltage and currents are, so voltage and currents are going to take it as the voltage always leads, because RL case voltage is always leads the current, at an angle of 5 degrees. Then the power factor of the system should be lagging only still. So because the voltage leads means the current is lags, that's why the power factor should be lagging. So then the case number 2, so means when the XL is less than XC, when the XL is less than XC, so that is the term XL minus XC is negative. So because this term only we have to consider, that's why the XL minus XC term is negative. Then the phase angle should be also negative. So the whole circuit, I mean the whole RLC series circuit should behave like a pure RC series circuit. So based on this one, so the V always lags the current at an angle of 5 degrees. So then based on this one, the power factor of the network should be, so it is leading. So because the voltage is leading means then it is, the current is leading means then the power factor of the system or power factor of the network should be leading nature. Then case number 3, last case it is. So then when XL is equal to XC, that is the term, that is XL minus XC equal to So 0 means it is 0 only. Yeah, XL minus XC also 0 only. XL equal to XC means XL minus X term is going to get 0. Then the power factor of the, the phase angle of the phase angle of the network should be 0. So phase angle of this network 0 means the whole RLC series circuit should behave like a, so pure resistive network. Then the voltage and currents are in same phase or within the phase. So voltage and currents are in the same phase or both are in same phase. Then the power factor of the corresponding circuit should be unity. It is because in case of the pure resistive network, the voltage and currents are both are in phase. Means the power factor angle should be 0 means then cos pi value becomes 0. Unity means unity power factor maintained by the RLC series circuit in this case. So these three conditions are going to consider based on the impedance offered by the network. So if it is a this case, then the power factor should be lagging. So if it is this case, then power factor should be leading, and in this case, then the power factor should be unity. So this is the end of the session. In this session we have discussed about till now. So then how much amount of current current given by the network, that is I equal to V by Z. So we have applied some voltage, based on that some amount of resultant current is circulating. So that is I equal to V by Z. Then based on this one, the phase angle of the network also we got, that is a tan inverse of, so it is XL minus XC upon R. Then based on this one we also find the average power taken by this one, so that is a VI cos phi, that is a resistance power only. So this is the average power taken by the network. So and based on this one we got the some phasor diagram of the voltage and current. So for that, so the voltage, the current of the network, take it as a reference. So it is always lags the voltage at an angle of 5 degrees. This is the phi. This is the voltage. So voltage always leads ahead the current at an angle of 5 degrees. So then based on this one we have considered the three different cases. So based on the impedance offered by the network, then XL is greater than XC means, so the corresponding circuit power factor should be lagging. Then whole circuit should behave like a RL series circuit. So the based on the impedance offered by the network, then XL is less than XC. XL is less than XC means the power factor is leading. Then the system or circuit should behave like a RC series circuit. Then third case, so based on the impedance offered by the network, the third case is XL equal to XC, means the power factor is unity we can consider. Then the whole network should behave like a pure resistive network. So this is the these many things we have discussed in this session, that is current, power factor, average power, phasor diagram of the network, and also three different cases. So consideration of the RLC series circuit based on the impedance offered by the network. So this is the end of the session. So in the next session we are going to discuss about the problem based on the RLC networks. So thank you and all. Thanks for watching the session.